Welcome back to the Deep Dive. Today, we're cracking open a source called It's All Energy.
Mm-hmm.
And we're really aiming to perform let's say, a surgical extraction of knowledge here.
Right.
We're not just after simple definitions. We want to get at the mechanics, what links everything together.
Exactly.
And that cover image they use, the roller coaster,
Yeah. It's a great visual, isn't it?
it just hits you immediately. Energy drives transformation, movement, force. It's all there.
And that transformation, that's really the heart of our deep dive today.
Okay.
Our mission really is to set up a concise but still sophisticated framework. For you listening, we want you to grasp not just the energy exists, but how this single fundamental idea makes everything happen around you.
Through constant change, right?
Through constant conversion and transfer. That's the key. No information overload, just the core concept.
Okay, let's unpack this right away then. If we
Yeah.
boil it all down, what's the single core definition of energy in this source?
It really boils down to function. Energy is defined as the ability to do work.
The ability to do work.
It's the potential or the actual action needed to cause any kind of change.
So movement, warming something up, making noise.
Exactly. Any change at all. That's the engine driving things.
And it's everywhere. The source makes that clear. We're using it constantly.
Mm-hmm.
When you walk, talk, even think, you're using energy.
Absolutely.
We're just surrounded by it.
Right.
You mentioned carnival rides or even something simple like popcorn popping.
And what's so interesting is how different those things seem, right? A light bulb, a loud noise,
Yeah.
someone running.
Yeah, completely different.
But fundamentally, they're all manifestations of the same thing. Energy, just
Yeah.
in different states, different forms.
Which leads us straight to that crucial concept the source really hammers home, conversion.
Yes.
Why is understanding conversion more important than just, say, listing the different types of energy?
Well, because conversion isn't just a feature of energy, it's like the universal law governing it. The absolute defining characteristic is that energy can't be created or destroyed. It can only be converted from one form to another.
Right, the conservation principle.
Exactly. Think about that roller coaster again. Why does it work?
Well, it gets pulled up high.
Right, storing potential energy. And then,
Then it drops, and all that stored energy becomes movement.
precisely, potential converts to motion. That interchangeability, that conversion process, is far more important to grasp than just memorizing the 6 specific forms we're about to go through.
Got it. So they're all just energy wearing different hats, essentially.
You could put it that way, yeah. Different organizational costumes, as you said.
Okay, so let's look at these 6 forms then. Starting with the one that makes that roller coaster so dramatic, motion energy.
Motion energy. It's pretty straightforward, really. It's the energy of movement, formally kinetic energy.
So anything moving has it. A plane, a falling leaf.
A speeding truck, yeah. Anything in motion possesses kinetic energy.
And the source makes a really specific point here. For you listening, 2 factors increase motion energy. Speed and mass, or weight.
Mm-hmm.
But they don't contribute equally, do they? That's a key distinction.
No, absolutely not equal. And this is where it gets a bit more sophisticated. Both speed and mass add to the energy, sure.
Right.
But the sources kind of implicitly stress that velocity, the speed, plays a much bigger role in ramping up the total energy compared to just the mass.
So that example they use, the fast truck versus the book falling off a table, what's the deeper point there?
It's really illustrating the multiplication of impact. The truck has way more motion energy than the book.
Yep.
And yeah, part of that is because the truck is much heavier, obviously. That's the mass factor.
But the speed.
But the fact that it's moving much, much faster, that's
Yeah.
where the energy really multiplies significantly. It's that speed factor that escalates the total energy involved so quickly.
Which is critical when you think about things like momentum or, well, safety.
Absolutely vital.
Uh-huh.
It really deepens how we need to think about the mechanical world.
Okay, that makes sense. Let's shift gears. Let's talk about the form known for being easy to move around, the one that basically built the modern world. Electrical energy.
Ah, yes. Electrical energy. Fundamentally, it's the energy of moving electric charge.
Powering everything from a lamp to huge factories.
Right. And while you have natural examples like lightning, which is just raw
You
electrical
see
power,
a dramatic example.
very. But the real breakthrough was when people figured out how to generate it reliably.
And what's the key thing the source emphasizes about moving it? Why is its ability to travel long distances such a game changer?
It's all about the efficiency of that long-distance transfer.
Okay.
Think about it. You can have, say, a huge power plant, maybe using the motion energy of a spinning turbine.
Driven by water or steam or whatever.
Exactly. Convert that motion directly into electrical energy and then send it hundreds of miles through power lines.
With relatively little energy lost along the way.
With surprisingly minimal loss, yes. That ease of transfer is what connects faraway energy sources to where we actually use the power. It underpins modern society.
But the source immediately follows that up with a big warning sign. Safety.
A crucial caveat.
Why the specific focus on investigating electrical safety right after praising its efficiency?
Well, precisely because of that power and efficiency we just talked about. Unlike some other energy forms that might dissipate or spread out, the electricity in those transmission lines is incredibly concentrated and powerful.
High voltage.
Very high voltage, needed for efficient transfer. And that poses an immediate serious danger if it's not handled correctly.
So the source is saying that investigating safety, updating protocols, it's not optional.
It's absolutely non-negotiable. It's a fundamental requirement for keeping that massive, efficient electrical grid running safely.
That link between the power of transfer and the absolute need for safety investigation, that's a really important high-stakes point. Okay, so we've covered mechanics and infrastructure. Let's pivot. Let's talk about the energy forms that shape our senses, our internal systems, starting with thermal energy.
Right. Thermal energy, people often just think of it as heat.
Yeah, that's the common idea.
But it's actually deeper than that. On a molecular level, thermal energy is really motion energy again.
Motion, how so?
It's the motion energy of the tiny atoms and molecules that make up a substance. The hotter something is,
The faster its molecules are moving.
exactly, they're vibrating, moving around more rapidly. That increased microscopic motion is what we perceive as higher temperature, and it means that the substance has more thermal energy.
Okay, so back to transfer, the example. Heating cold chocolate milk on a stove. We're transferring that molecular kinetic energy.
Precisely. You're taking another energy form, maybe chemical energy from burning gas, or electrical energy heating an element.
Right.
Converting that into intense thermal energy in the stove itself. Then that thermal energy transfers, mostly by conduction, to the milk molecules,
Speeding them up.
speeding up their vibration, raising the milk's temperature, and when it cools down later, it's just losing that energy, that molecular vibration, back out to the cooler surroundings.
Fascinating. Okay, let's quickly cover the last three forms. Sound energy first.
Sound energy. Every single sound you hear is this form of energy traveling into your ears.
And it's another conversion chain, isn't it?
Yes, typically. It's essentially mechanical energy, like a vibrating guitar string or speaker cone creating pressure waves that travel through the air or water or solids.
And louder sounds just have more energy.
They have greater amplitude, yeah, more energy packed into those waves. But whether it's a tiny whisper or a blasting trumpet, the basic physics energy transferred via vibration and pressure waves is the same.
Okay, and then light energy.
Light energy, the electromagnetic radiation we see from the sun, lamps, screens.
Obvious sources.
Right. But the crucial function highlighted in our source isn't just that it lets us see.
Oh.
It's its role as the primary energy input for the biggest energy storage system on Earth.
You mean photosynthesis? Plants using sunlight.
Exactly. Light energy is how that radiant energy from the sun gets captured and essentially prepped for conversion into stored potential energy.
Which brings us perfectly to that storage form, chemical energy. The energy locked away inside things.
Precisely. Chemical energy is potential energy stored within the chemical bonds holding atoms and molecules together. It's like the battery for both life and technology.
And what's the key takeaway about its applications, according to the source?
I think the most striking point is its universality. Chemical energy powers us, our bodies, but it also powers a car engine.
Right, same fundamental type of stored energy.
Exactly. The energy in an apple, that's chemical energy. Your body breaks those bonds, converts it to motion energy when you move, and thermal energy to keep you warm.
And burning wood. Or gasoline in an engine.
Same idea. You're triggering a rapid chemical reaction, breaking bonds, releasing that stored potential energy very quickly, converting it instantly into a lot of thermal energy and often motion energy too.
Amazing how interconnected it all is.
Yeah.
Okay, so let's bring it back to our goal for you, the listener. Hopefully, you now have a clearer, more connected framework for understanding energy. We've gone beyond just listing names. We've focused on that central idea of conversion.
Right.
Using those 6 forms, motion, electrical, thermal, sound, light, and chemical, really just as examples of that constant change.
And if you zoom out, that constant dynamic flow, that constant change, is literally what makes the entire world function.
It's never static.
Never. Energy is always either changing form or changing location. That roller coaster image we started with, it sums it up perfectly.
Potential to motion.
Motion converting to heat through friction. It's all governed by that inescapable principle of conversion.
So the takeaway message,
Yeah.
when you leave this deep dive, what should you be thinking about? Maybe next time you do something simple, like plug in a hairdryer or put on headphones to listen to music.
Yeah.
Remember the hidden complexity there. It's not just a device working. It's a whole engineered chain of energy conversions and transfers happening.
And happening safely and efficiently, hopefully.
Right. Which leads to a final thought,
Okay.
something provocative for you to consider on your own.
Let's hear it.
Well, the source really stressed how efficient electrical energy transfer is, but also how vital investigating its safety is.
Definitely.
So think about this. If our modern world depends so heavily on converting other energy forms, chemical thermal motion, into electrical energy, just so we can distribute it easily.
Right, and then converting it back again at the other end for use.
Exactly. How much of our global infrastructure, our governance, our politics even, is really just a massive, incredibly complex system built purely to manage and safeguard these nonstop energy conversion chains?
That's a deep question. You're talking about the sheer scale of the resources, technical, political, economic, dedicated just to keeping that flow of energy converting safely and reliably.
Yeah. What does it truly take to manage that constant essential transformation? Something to think about.